I'm very excited to be talking about my favorite topic, which is binaries. And hopefully tonight I'll be able to convince you that 2 is in fact better than 1. All right, so if you remember nothing else from my talk tonight, I want you to remember that binaries are everywhere. Binary systems are systems of 2 astronomical bodies of the same kind that are comparable in size. And objects of all masses are found in these pairs. For instance, this is the asteroid 243 Ida, and it was thought to be single until it was imaged by the Galileo spacecraft. When scientists studying this asteroid took a closer look, they actually found this tiny little baby asteroid orbiting it. It had its very own little moon that they named Dactyl. So the radius of Ida is about 16 kilometers. The radius of Dactyl is only half a kilometer. It's just a little guy. But much more massive objects form in these binaries too. This is a computer simulation showing the collision of 2 black holes that was detected by LIGO. LIGO detected the gravitational waves, or ripples, in space and time that were generated as the black holes spiraled in towards each other, collided, and eventually merged. The simulation shows what the merger would look like if we were able to be up close and personal with it and see it with our own eyes. So eventually even the Milky Way might be part of a binary system. Over the next several billion years, the Milky Way will make its way towards the Andromeda Galaxy. At a certain point, they could be close enough that they begin to orbit one another and temporarily form a binary galaxy system. Sometimes even siblings form in pairs. Everyone say hello to my sister Victoria.
Hi, Victoria!
As you can see, our compositions are quite similar. She's been orbiting our common center of mass for the past 27 years, and having her as a companion has made those years much less lonely. The sun, however, is not as lucky as me. The sun is lonely. We only have 1 star in the solar system. But systems that with more than 1 star are actually quite common. About half of the sun-like stars that are out there form in these binary systems. For the most massive stars, 80% of more of them are found in these binary systems. So we even know 2 septuple systems. These are systems with 7 stars in orbit around one another. This is the architecture of one of these systems, New Scorpii. So this is pretty weird, right? Like, we're used to 1 star, we're used to our sun in the solar system. So how do these systems of 7 stars even form in the first place? And why are some single when others are not? So stars form in a region of gas and dust called a molecular cloud. When overdense regions of the cloud become too massive, they collapse under their own gravity, fragmenting the cloud. These fragments aggregate more material until they are massive and hot enough for hydrogen fusion to occur. When this happens, a protostar has been born. If the conditions are good enough for 1 star to form, then others will surely follow. So these protostars often form in groups of 10 or even more. But systems with more than 2 stars are dynamically unstable. And so the stars will disperse or be ejected, eventually leaving us with a system of only 2 stars or just 1, like the sun. All right, so now we know that binaries are everywhere and why they form that way. And because they're everywhere, it's important to understand them for an overall understanding of the solar neighborhood and eventually the Milky Way as a whole. But how exactly do we do that? And unfortunately, the atmosphere is our enemy in this endeavor. It's pretty nice for those of us here on Earth if we want to be able to breathe or whatever, I guess. But if we're trying to look at multi-star systems, it kind of gets in the way. So when I tell people that I'm an astronomer, and that I get to look through telescopes for a living, they often have this romantic notion that this is what I get to look at when I stay up at the telescope all night. And they're often quite disappointed to learn that the stars we observe look a little more like this. So it's not that attractive, right? So stars look like this through a telescope because hot and cold cells make the atmosphere turbulent. This turbulence distorts the starlight from distant stars and creates what's called a speckle pattern that you can see here. So this GIF shows how the star's speckle pattern changes and moves about depending on how the atmosphere is distorting the wavefront. So all of these changes shown here in this GIF are occurring in less than a second. So they're happening super, super rapidly. And so how can we tell whether this very fickle, very blobby mess is 2 stars or just 1? So I use a technique called speckle imaging to resolve this blobby image and to see the 2 stars that are actually there in the system. So when we observe with a speckle imager, we take 1,000 photos of this star. And the exposure times for these photos are very short. They're like 40 milliseconds long. And the reason that we do that is because that's about how long the atmosphere stays in the same state. And so this gives us an understanding of how the atmosphere is changing with time so that we can eventually remove the atmospheric interference from our data. And so once the atmospheric interference is gone from our blobby mess, we can see that it's actually 2 stars that are super close together. So I threw these slides in at the last minute because I was actually observing last night at the telescope. And sometimes we do get to see things that are a little bit prettier. So last night I was observing with the 200-inch Hale telescope at Palomar Observatory. It's near San Diego. You should go visit it sometime. It's super cool. So does anyone know which planet this is? Uranus, correct. All right, so last night we were imaging Titan, Neptune, and Uranus, looking at how their weather changes over the course of their rotation periods. So on the left you can see that, well, maybe you can't, I don't know. From here you can see that part of Uranus is illuminated from the sun, part of it's not. And on the right you can see its really cool ring system and one of its moons, I think it's Ariel. And so Uranus rotates on its side, probably because of a collision sometime in its past. And so we get this really spectacular view, face-on view of its ring system. So for comparison, this is the JWST image of Uranus that was taken last year. You can see some of the same attributes from what we see in our telescope and what they're seeing in space. And so I think it's pretty cool. You know, it's not quite the same, I will give you that. But I think it's pretty cool that we can still see some of these same features from the ground through the atmosphere. All right, so once you've used these techniques like speckle imaging to figure out which stars are binaries, we can then start tracking down Tatooines. In the Star Wars franchise, Tatooine is a harsh desert world that orbits twin suns. And it's the homeworld of Luke and Anakin Skywalker. Got some Star Wars fans here. But the double suns of the planet Tatooine are not just science fiction. They actually are really out there in our galaxy. So Kepler 16b is one of these Tatooines. It's a Saturn-mass planet composed half of gas and half of rock and ice. It orbits in the habitable zone of its host stars, but its temperature is comparable to that of dry ice, so I wouldn't really recommend taking a vacation there if you're looking for a place to go. All right. So there are 2 types of planets in binary systems. There are circumstellar planets, where the planet orbits just one of the stars, and then there are circumbinary planets, where the planet orbits both of the stars. Both Tatooine and Kepler 16b are examples of circumbinary planets. So although we know that these planets and binaries are out there, they can be quite challenging to find. Most planet detection techniques are much less sensitive to planets in multi-star systems. And this is true for a few reasons. So as I showed before, the atmosphere makes it hard to resolve the 2 stars in a multi-star system in a close binary. And the additional light from the stellar companion can distort or completely hide the signal from a planet. And even if you do detect a planet in the system, you might not be sure which planet or which star the planet is orbiting. So this can be seen for planets detected using the Transiting Exoplanet Survey Satellite, or TESS. TESS monitors the brightness of many stars at once, looking for dips in that brightness. These dips are indicative that a planet is crossing or transiting in front of its host star. The light from a secondary star can cause the dip we observe to be shallower than the actual true dip. So on average, this causes the planet's radius to be underestimated by a factor of about 1.5. And if instead the planet is orbiting the fainter second star in the system, the planet's radius might be underestimated by a factor of 3. And so this has really major implications if we're trying to find other Earth-like planets out there. You might think you found a rocky Earth-sized planet, but when you take into account the light from the stellar companion, it's actually more like a gas planet. So stellar companions can also hide the planets completely. This video shows that smaller planets transiting in front of their host star create a shallower dip than the larger planet. And so if the secondary star is contributing light as well, then the dip from the small planet could be completely obscured and you might not detect a planet in the system at all. So because of these challenges, only a small fraction of the known exoplanets have been found in systems with more than one star. And an even smaller fraction of these are circumbinary. So this chart is not at all representative of the fact that we know that half of planet-hosting stars are in binaries. And so if we want to fully understand planet demographics, we need to confirm the planets in the multi-star systems. But if we want to confirm the planets in the multi-star systems, we have to get a little bit creative about how we're going to detect and characterize them. So that is what SHIRA hopes to do. SHIRA is a new mission concept that's going to be used to survey 48 sun-like stars in nearby binary systems. SHIRA is going to look for small planets in the habitable zones of their host stars by very closely monitoring the path of the stars across the sky. So if you measure the positions of stars in a binary system very precisely, you might see them deviate from what you expect their path to be. This deviation can be caused by a planet in orbit around one of these stars. The planet is exerting a gravitational influence, a pull on its star, taking it out of its expected path. And so the amount that the star is wobbling away from its expected path tells you some of the characteristics of the planet. It tells you a little bit about its mass and about how close it is to its host star. If it's more massive or closer to its host star, then the star will wobble a bit more. And so this technique is called astrometry. And astrometry has been used to detect 3 planets so far. It's not super popular yet, but upcoming missions like Gaia are going to find a lot more of planets like this, and SHIRA is going to as well. So SHIRA will be sensitive to giant planets around all 48 of the stars it's going to observe. It'll be sensitive to sub-Neptunes around 27, super-Earths around 15, and Earth-sized planets around 2 of these stars. So this means that SHIRA could find the first Earth-sized planet in an Earth-like orbit around a sun-like star. So SHIRA will also constrain the rate of planets in multi-star systems and tell us what these planets are like in comparison to the single-star systems. So in general, missions like SHIRA give me hope that we might actually begin to figure out what the planets in multi-star systems are really like out there. Okay, so to summarize, binaries are everywhere. Regardless of mass, astronomical objects are going to be found in binary systems. But the atmosphere is kind of mean sometimes. It makes it difficult to detect these binaries. And so we have to get a little bit creative about how we search for these binaries and how to understand the planets of these multi-star systems. And if we do that, then we can track down all the Tatooines that we know are really out there in the Milky Way. So thank you so much for your time, and I'm happy to take... So we have a question. What is the longest duration of a binary system that we've been able to found? So we found them in all varieties. Some of them are as short as less than a day. Some of them are tens of thousands, hundreds of thousands of years. And so, yeah, binary stars, if it's more widely separated,